Okay, so now that we have basically all of the values related to this circuit ready, we can do some calculations. And so let me see if I can use any of these papers over here. I don't know. Okay, so I have basically, so the circuit that I had was this circuit over here. That was a circuit like this. I had a capacitor, I had a resistor over here. And this goes to ground. This is my V of out. This is my V of in. And we had a sine wave in the sine wave over here. And V of in was equal to 19 volts peak to peak. And the frequency was 10.677 kilohertz. And the value of this capacitor was 0.01 microfarad. The value of this resistor was 1 kilo ohm. And that's basically all I know about this circuit. Now, in order to calculate the output voltage on this point, meaning that the output voltage on this resistor, what you need to do is it's just simply like, it's pretty much like Ohm's law, but a little bit different in an AC circuit. So what you need to do is that basically, if you were working in a circuit, in a DC circuit, you would use the Ohm's law, which is equal to V is equal to IR. And the voltage drop across this resistor would be, for example, there would be some voltage drop across this resistor, some voltage drop across, for example, if this was a resistor, across this resistor, and then that way this would be a voltage divider circuit, and that way you would calculate the voltage across these two basically these two components, meaning that, let's say that you had a resistor over here and resistor over here, and a power supply, for example, something like this, and this would be your V of S, this would be your R1, this would be, for example, your R2, and this voltage over here would be V of R1, and this voltage over here would be V of R2. Okay, and in this circuit, what would happen is that you would, V of S would be equal to V of R1 plus V of R2. This is the Kirchhoff's law of voltages, or whatever that is called. Now this is in a DC circuit. Okay. Now in an AC circuit, it's pretty much the same thing, except that and in order to basically calculate these voltage drops across these resistors, V of R1 would be equal to basically R1 to R of equivalent times V of in, or V of S, basically the same thing. And V of R2 would be equal to R2 over R of equivalent times V of in, right? So, and of course, you know that R of equivalent in this circuit would be equal to R1 plus R2, because this is a series circuit. So then V of R1 would be equal to R1 over R1 plus R2 times V of in, and V of R2 would be equal to R2 over R1 plus R2 times V of in, That way you would be able to calculate the voltage drops across these two resistors. Now in an AC circuit, which is basically the circuit that we have over here, let's say that this is V of in and this is V of out. In an AC circuit, instead of this R of equivalent, what we have is something called the impedance. And the impedance is basically the sum of all resistances to electric current to electric current in this circuit, and that is denoted by Z. And Z, basically the formula is in this kind of RC circuit is going to be equal to X of C squared plus R squared, the square root of X of C squared plus R squared. Now X of C is actually the reactance of this capacitor. So what that means is that basically this resistor over here has some ohmic value in this circuit, and so does this capacitor, meaning that when there is current in this circuit, this acts as a resistor, and of course this is a resistor as well. So when you calculate the reactance of this capacitor, what that means is that you are basically considering this capacitor as a resistor, and then the reactance of that capacitor is going to be the ohmic value of this capacitor in this circuit at that particular frequency. And X of C is equal to 1 over 2 pi F C. So 2 pi is just constant, F is the frequency, and C is the value of your capacitor. So that's that, and that you would get in ohm, right? And then this also you would get in ohm as well, because this is also impedance. So that's the same thing. So now what I need to do is come over here and first calculate the reactance of this capacitor in this circuit. So X of C is equal to 1 over 2 pi. All the time I just make this mistake, 2 pi over FC. Now the frequency was 10.677 kilohertz times 10.677 actually kilohertz times 10 into 10 raised to the power 3 hertz times C, which is basically the value of my capacitor here was 0.01 microfarad. So 0.01 microfarad times 10 into 10 raised to the power negative 6 farads. So if you simplify this a little bit, you would get, so 10 raised to the power 3 and 10 raised to the power negative 6 would be 10 raised to the power negative 3. And then 0.01 times, for example, times 10 would be 0.1, and 0.1 times 677. What is this thing? No, this is 10.677. Sorry. This is 10.677. Okay, so 0.01, this is 10 raised to the power 2. This is 10 raised to the power 2, and so this would be 10 raised to the power negative 1, and 10 raised to the power negative 1 times this number would be 1 over 2 pi times, for example, 10 raised to the power negative 1 would be 6.77. So that would be X of C in this circuit. Now if you calculate this, you would get 1 over 2 pi times 106.77, which is equal to, which makes no sense. It's too large a number. I think I made a mistake over here, so let me do this again. So if it's 1 over 2 pi, sorry, 1 over 2 pi times 2 pi times fc. So the frequency was 10.677 kilohertz into 10 raised to the power 3 hertz, and times the c, which was 0.01 microfarad, times raised to the power -6, and that's, this number is right. This is 1490.6335, and so on and so forth. This is, somehow I made a mistake over here, so this is equal to 1490.63 approximately ohm. So this is the reactance of this capacitor in this circuit. I'm going to give this to, save this into, for example, this memory over here, shift store A, so that if I need it again, I can use it for other parts of the calculation. Okay. So what that means is that this. So what that means is that my x of c over here is equal to approximately 1490.63 ohm, and I have saved that in memory A, right? So that is one thing. And then the impedance in this circuit, is equal to the square root of x of c squared plus r squared. So that is equal to the square root of this number over here, 1490.63 squared plus r squared, which is basically 1000 ohm resistor. I take it as 1000 squared, and that would be the square root of A. I saved that number in A squared plus 1000 squared, which is 1794 times 0.9897. So I take it as 1794 point, for example, 98 or 99, for example, right? 99 ohm. And I save this into shift store B. So the value of impedance, or Z, is equal to 94.99 ohm, and I have saved that to B. So now what this thing is, the impedance that I have calculated here, is the total resistance to electric current in this circuit, meaning that the resistance that this capacitor has in this circuit, plus the impedance of, plus the resistance that this resistor has in the circuit. The total thing basically put together is around 1800 ohms, right? And this reactance that we have calculated here is actually the opposition to the flow of electric current in this circuit, basically taking place or done by this capacitor, which is the reactance of this capacitor, and both of them are basically measured in ohm, right? So that is that. And now what you want to do, basically, in order to find the voltage drop across this resistor, which is your V of out, we do kind of the same thing that we do in the case of a DC circuit, meaning that V of out in this circuit is equal to the value of the resistor, which is 1000 ohm, divided by the total resistance in the circuit, which is my impedance. So my impedance was something around 1794.99. Okay, so and if you pay attention to what I did here, was that, for example, when I wanted to find the voltage drop across this R2 over here, V of R2 was equal to the value of R2 divided by the total resistance in the circuit times V of in. So now here again, I want to calculate the voltage drop across this resistor. I've taken the ratio of the resistor itself to the total resistance in the circuit times V of in. So V of in is equal to 19 volts peak to peak times 19. So if I calculate this over here, it's 1000 divided by the impedance, which was stored in B, times 19 volts peak to peak, which is 10.585 volts, which is 10.585 volts peak to peak, That is your V of out. Now, if you remember, we actually measured the same thing on the oscilloscope, peak to peak, the peak to peak signal we measured on the oscilloscope, and we found out that the V of out, which was the V of R, was equal to 11 volts peak to peak, and this is 10.58 volts. So it's kind of the same thing. There is no problem there. And that's basically that. Now, one more thing that we need to do here is find the voltage drop across the capacitor, which is something that we couldn't do with the oscilloscope, because we would basically short this resistor out. So that was not possible with the oscilloscope. So what we did, basically, we used an RMS multimeter in order to measure that voltage across the capacitor. So, and you see that in this kind of circuit, in this kind of DC circuit, the voltage supply is always equal to the voltage drops across each of the resistors in the circuit, meaning that your V of S is equal to V of R1 plus V of R2, the voltage drop across R1 plus the voltage drop across R2. Now the kind of the same thing happens here as well, meaning that in this AC circuit, V of in is equal to V of R, with the voltage drop across the resistor, plus the voltage drop across the capacitor, but then you have to square everything. So V of in squared is equal to V of R squared plus V of C squared. Kind of the same thing, but you have to square everything. So that means that this was basically 19 volts peak to peak. So 19 squared is equal to V of R, which is basically the voltage across the resistor, or V of out, which was 10.585 volts peak to peak, 10.585 volts peak to peak, all squared, plus V of C squared. So that means that V of C squared is equal to 19 squared minus 10.585 squared, and so what that means, that V of C is equal to the square root of 19 squared minus 10.585 squared, and that is equal to That is equal to square root of 19 squared minus 10.585 squared, and that is equal to 15.778, which is equal to 15.778 volts peak to peak. But now the problem here is that the voltage that I measured across the capacitor, this is the voltage across the capacitor. The problem is that the voltage that I measured across the capacitor was 5.31 volts RMS, not peak to peak. Okay, so now we need to see if basically this calculation is right or not. And in order to do that, what you need to do is that you need to know a little bit about the RMS voltage and the peak to peak voltage and the peak voltage. So what that is that if you have a sine wave, if you have a signal over here, and the sine wave, so for example you have pi by 2 pi, 3 pi by 2, and 2 pi. So at pi by 2 you're at, for example, you're at 1, and then you go to 0, -1, and 0. So when you have a sine wave, you have some situation like this as we saw before. Okay, so this is, let's say that this is your signal. Okay, now, and suppose that this is basically what you see on the oscilloscope screen, and this is your signal. So the peak of your voltage up here, and this peak of your voltage down here, the voltage across these two peaks is basically called V of peak to peak. This peak to peak, this is the peak to peak voltage, or V of PP. The voltage from the reference line, or from the zero line to this peak over here, is called the peak voltage, or V of P, and it's the same thing as this voltage over here, because this wave is symmetric, so that is also V of P. And there is some voltage over here, around 60-70% along the way between the zero line and the peak line over here, which is kind of this 60-70% up here from the reference line, and that is called V of RMS. This is the RMS voltage. Now it's important to understand the relationship between these three voltages. So you have V of peak to peak, you have V of peak, and you have V of RMS. And you see that basically the peak to peak voltage is 2 times the peak voltage. So V of PP is equal to 2 times V of P. And the relationship between the V of RMS and V of P is that V of P is equal to V of RMS times the square root of 2. Square root of 2 being 1.414 or something like that, 1.414. So if you multiply this V of RMS by square root of 2, you will get V of peak. And if you multiply V of peak by 2, you will get V of peak to peak. Okay, so that is that. Now, you need to use these. Basically, first you need to understand these two formulas, and then you need to use it in order to find out whether our findings were correct or not. So we said that V of C was equal to 5.31 volts RMS, and also we calculated the V of C as 15.778 volts peak to peak. I want to see if that's actually correct. Okay, so let's take, for example, 5.31 volts RMS. Let's see if that's actually equal to 15.778 volts peak to peak. So since you know that V of peak is equal to V of RMS, times square root of 2, and here I have V of peak to peak and RMS, so I have to somehow write V of peak as, so you know that V of peak is 1/2 V of peak to peak, because V of peak to peak is 2 times V of peak, so you can write V of peak as 1/2 V of PP is equal to V of RMS times square root of 2. So what that means is that V of peak to peak is equal to this whole thing, V of RMS times square root of 2 divided by 1/2 divided by 1/2. I think I've made some sort of mistake here, hopefully not. So basically V of peak to peak is going to be equal to, so V of peak to peak is going to be equal to V of RMS times square root of 2 divided times the reciprocal of this, which is 2 square root of 2. So 2 square root of 2 V of RMS. So I think you can use this formula in order to see whether these two voltages are correct, right? So now my V of peak to peak is 15.778 volts peak to peak, right? So that has to be equal to V of RMS times 2 square root of 2. The V of RMS is 5.31. So if I write 5.31 volts times 2 square root of 2, that has to be equal to this voltage. So 5.31 times 2 square root of 2, as you can see, it's equal to 15.01. 15.01, the same voltage over here. Okay, so you can use these formulas over here. Of course, the only important thing here is that you understand that it's easy to understand that your peak to peak voltage is 2 times your peak voltage, and then the only and your RMS voltage, if you multiply it by square root of 2, you get your peak voltage. That's the only thing that you need to understand here. So that's basically that, right? So we have no problem here with V of C. That's already taken care of. This was also okay. This was also okay. This was also okay. I'm not going to get into the current, because I actually, to be frank with you, I really don't know how to convert between the RMS current and peak to peak current, because the current that we actually measured with the multimeter must be the RMS current, and it's not the peak to peak current. So I'm not going to get into that, right? So the only thing that remains here is the phase angle, here, and that needs a little bit of explanation. So the phase angle over here, there is something called the Phasor diagram that we need to know about these AC circuits. So if you're familiar with vector diagrams, it's basically a Phasor diagram. A Phasor diagram is some sort of vector diagram that has been used in order to understand the relationship between the current, the voltage, and so on and so forth in these circuits. And so you have this vector over here, which represents V of R, the voltage across the resistor, and you have this vector over here that represents V of C, the voltage across the capacitor, and there is a 90-degree angle between these two. And then if you connect these two, this way, your V of in is going to be between these two vectors. That is going to be your V of in, that's your input voltage, and that's going to be your current that goes through the circuit. So you see that and what's important here to understand is that your V of R is leading V of in, and also V of in is leading V of C, and also said in another way, if I want to confuse you, V of C is lagging V of in, and also V of in is lagging V of R. And also there is a 90-degree angle between the current going through the circuit and the voltage that is across the capacitor. So this current is actually going through the resistor and also through the capacitor. But the phase difference between the current and the voltage across the resistor is 0. These are actually basically principally practically the same vectors, but the voltage across the capacitor and the current going through the capacitor, there is a 90-degree angle between that, and you get these two angles over here. You can call this theta, and you can call this, for example, phi. You can call them anything that you want, as long as you understand what you're doing yourself. And here again you need a little bit of trigonometry. Usually we use the tan function in order to calculate this angle theta, and then since we know that the whole angle is 90 degrees, then this angle phi, if you know your theta, you can calculate your phi, right? So we said that tan of an angle, if you have this, for example, if you have this triangle over here, if you have this theta, your theta over here, tan of theta is going to be equal to the opposite side by the adjacent side. We already talked about that when we were talking about trigonometry. So now over here, this is a right triangle, and this is your theta. So here your tan of theta is going to be equal to the opposite side, which is basically V of C. So this opposite side is this length, which is equal to this length, and that is actually V of C, to the adjacent side, which is actually V of R. So if you have these two values, you can always find your tan of theta. And also there are two other formulas here that I need to find first myself. So this is 1 over 2 pi, and there is also these two formulas. I do not really, it must have taken them a whole long time to come up with these formulas, but these are actually very neat formulas. Let me actually get rid of this thing over here. Okay, there is this formula over here, which is 1 over 2 pi FRC, 1 over 2 pi FRC. You can use this formula as well. And also tan of theta is equal to x of c, I think, by r, the reactance by your resistance. So you can use these three formulas whenever you need to calculate your theta. And remember that by theta here, what is meant here is the angle between V of in and the voltage going through your resistor, not going through but across your resistor. So you want to actually learn this Phasor diagram, and so that you don't mix up these two angles, because it's important to understand which angle you are actually calculating. Okay, so now what we were doing in this circuit, the circuit that we had here was basically this circuit over here, and we got some sort of angle here that if I can find it. So the circuit that we had was this circuit over here, and we were actually monitoring the voltage across this resistor and also the voltage on the input, right? The input voltage. So we were actually monitoring this voltage V of in and also the voltage across the resistor. So if I calculate this theta, that theta is actually the phase difference between those two voltages. And we found that the output, which was basically this V of R, leads the input by 54 degrees. And right now you can see that of course the output is leading the input voltage, and this theta was 54 degrees. So let's see if it's in calculation also 54 degrees. So I can use, for example, V of C to V of R. So tan of theta is equal to V of C, which was I calculated that somewhere over here, 15.778 volts peak to peak. The voltage across my capacitor was, I want to use the peak to peak voltage. We had also the RMS voltage for that capacitor, but I cannot use that RMS voltage because I'm also using the peak to peak voltage for the resistor, so you cannot mix them up, right? So the peak to peak voltage for the capacitor was 15.778. So V of C to V of R, which is equal to 15.778 volts peak to peak over V of R was the output voltage was 11 volts or 10 point something. It was 10.585 volts peak to peak. 10.585 volts peak to peak. So then these two will cancel out, and that gives you ratio, meaning that 15.778 divided by 10.585 is equal to 1.490 and so on and so forth. So approximately 1.49. So now this is tan of theta. This is tan of theta. So your theta is going to be equal to tan inverse of this ratio of 15.778 by 10.585. The tan inverse of this ratio. So I use tan inverse of that ratio is going to be equal to 56.14 degrees. 56.14 degrees. And that's actually, I think, the angle that we had over here. If I can find it, you see over here, I got 56 degrees, and the angle that we found over there and read on the oscilloscope was 54 degrees, so only 2 degrees difference. And one more thing that we can do here as well is that now that you know basically your theta, you can calculate your phi as well. You know that theta plus phi is equal to 90 degrees from here, so your theta is equal to 56.14 degrees plus phi is equal to 90 degrees. So your phi is equal to 90 degrees minus 56.14 degrees. So your theta is equal to 90 minus 56.14, which which is equal to 33.86 degrees. 33.86 degrees. And that is basically how much, the angle by which the V of in is leading V of C, right? That's basically what that means. So that's basically all that you need to know about, all the basics that you need to know about these RC circuits. I actually wanted to do another video about this circuit as well. So you see that the circuit that we were talking about, it was if I'm not wrong, I always mix this up. I don't know where that thing right now is, but well, we were actually talking about this circuit over here. So we had the capacitor, and then and the resistor going to ground, right? Resistor going to ground. So we were talking about this high pass filter. So we could do all of this thing about the low pass filter, and the difference between the high pass filter and low pass filter is that in the low pass filter you have the V of out is the voltage across the capacitor, and then if you have V of in over here on the horizontal axis and F of in and V of out on the vertical axis, the voltage is actually for low frequencies, the voltage is very close to the supply voltage, and as you increase your frequency, the voltage gets closer and closer to ground. Okay, and then you can use all of these formulas in order to work with this kind of circuit. So you use these kinds of circuits for different applications. That's basically the whole story. So I hope that you enjoyed these two videos, and I'll see you in the next one. Thank you.